Hi students, in this video we're going to look at some applications of differentiation, looking in this case at how to calculate instantaneous rate of change. Right, so by the end of this video you should be able to interpret the derivative as the instantaneous rate of change, and then also determine instantaneous rates of change. Right, key things to remember. So the formal definition of our derivative, so derivative f dash x, or sometimes also called dy dx, if we're talking about y equals some function of x. Remember, they both mean the same thing. That is equal to the limit as h approaches 0 of our function of x plus h minus our function of x divided by our value of h. This is basically our gradient formula, remember. And as h equals 0, that means our limit as h gets closer to 0, that's what we're talking about with our instantaneous rate of change. Now, we have also learned that there is a fast shortcut rule that we can know off by heart to help us work out the derivative of a power, which includes polynomial, function 2. So the derivative of a times x to the n, the derivative is the power comes to the front, which is n, then the power goes down by 1. And that's a shortcut way to help us find derivatives of power functions. Now, calculating the derivative of a function at a certain point is our instantaneous rate of change. So we've discussed that previously, but I just want to go over it again just to make sure we're 100% clear. The derivative is our instantaneous rate of change. Okay. Now, if we know the function, if we're given a function, we can determine the instantaneous rate at which quantities are changing by either using the relevant rule. At the moment, we just know the power rule, but as you go further through your maths, you'll learn other rules that make things a lot easier for you. If we don't know the rule to find the derivative or to differentiate, we can estimate it using our formal definition of a derivative and just using a really small value of h, and that can give us a really solid estimate for what the derivative might be. Right, so let's do some examples. So we've got a sample of radioactive cobalt, 60, that's decaying according to this function. And then CT is the mass of cobalt in grams, that's important. And T is the time since the sample was taken in years. And what we have to do is estimate the rate of radioactive decay here after 10 years. So that's about at this point here. Okay, so we'll need to work out how is our mass changing over time. Okay, what is the rate at which the mass is, by the looks of things, decreasing by? Right, so that tangent there has a negative gradient. The amount of mass of cobalt 60 we have is going down, so we can expect to have a negative derivative. Now, for this function, we don't have a rule yet for determining the derivative of this function. So what we're going to have to do is use our formal definition, c of t. In this case, we're using c, not f of x, because we're just given c of t, minus c of t over h, and I always forget my limits out the front here. Now, let's just consider our options here. So we've got c of 10, because we have to find the derivative after 10 years. And if we sub 10 in, we get 134.2444.881 grams. So after 10 years, we've got 134 and a lot grams. Now what I'm going to do is let h equal 0.000001. So a very small number. That's about it is a millionth. Okay, so quite small. And so now we're just going to use it in our formula. So we're going to find the amount of cobalt after 10.000001 years, and that's actually going to be 134.2444.705. So not a huge difference there. And only about 150, 200, whatever that is, close to millionths of a gram there. So in terms of finding out what our instantaneous rate of change is, so C dash at 10, we're going to subtract these values. 134.2444705 minus 134.2444881 all over our H value, 0.000001, which equals negative 17.6. Now in terms of our units, that's grams per year. Okay, so our sample is decreasing in size by 17.6 grams per year. That negative is what means it's decreasing, so we're losing mass, which made sense by looking at our graph. So students, there's an example where if you don't know the rule to derive our function, we can still use our old definition. We can use our formal definition of a derivative and a really small value of h to work out what the instantaneous rate of change is. Right, now second example, a ball is thrown from a tall cliff so that its height above the surface of the water below can be modeled by the following function, where ht is the height of the ball above the water in meters, and t is the time since the ball was thrown in seconds. And we have to determine the falling speed of the ball 4 seconds after it was thrown. So 4 seconds after it was thrown, so we're looking at this point here. Okay, and we're going to go from there. All right. Now, students, an important note on with this particular problem is that speed is the derivative of height / position. And really, it's not even speed, and that's the derivative. Physics students will get angry. It's actually velocity, which for our intents and purposes now is just going to be speed. So velocity has a direction. So what that means is if the speed is going to be positive, that will be going up. If the speed is negative, it'll be going down. As we saw in our previous exam on the graph, it looked as though the graph was going downwards, so we're expecting for this one a negative velocity. So our speed is actually going to equal h dash at 4 seconds. Okay, so our speed at 4 seconds will be the derivative of h with our number 4 subbed in. Right? So how are we going to work that out then? So h dash t, deriving this, 12t just becomes 12 minus, then 2 times 4.9 is 9.8. The power goes down from 2 to 1, and then our constant, all that disappears. So there's our derivative. So h dash 4 is going to be 12 minus 9.8 times 4, which is going to be negative 27.2, and that's going to be meters per second. So that's our rate. So h was in meters, t was in seconds, so our rate is meters per second there. And that one, again, nice and straightforward because we knew the equation and we knew we had a rule to derive it. So once we could derive it, we could get our speed, our instantaneous rate of change pretty easily. Right, students, so after watching this video, you should be able to interpret the derivative as the instantaneous rate of change. That's what all our examples are about, and also determine or calculate instantaneous rates of change as well.